Okay, now we go into the potential function, or the symbol is phi. Okay, the symbol here is phi. P-H-I-P. Okay, so what is potential function? Potential function is useful for the potential flow. Okay, and then what is potential flow? Potential flow is, let's say you have the flow around the cylinder. All right, you have a cylinder, and then you have a flow. All right, you have flow. The real flow is like this. It goes up and then this detach. It goes down and then this detach. Okay, this is the real flow. And then you have some vortex here. For the real flow, you have some vortex in front of this cylinder. Okay, this one is real flow. Okay, so what about the potential flow? Okay, let's say you have cylinder. Okay, and then you have the flow coming in the same way. It goes up and then it goes like this. Okay, same thing at the bottom. Okay, it goes like this. It's a simple flow, nor vortex nor rotation. Okay, it's go like this. Okay, this one is potential flow, where the flow is inviscid and irrotational. Okay, so in this subtopic we will learn regarding the potential flow, and then we will define what is the potential function. Why we need potential flow? Because it will simplify our equations, so we no need to solve the complex equation, but the result is of course different, but it's useful for engineering applications. Alright, so first we define what the vector identity. The curl of the divergence of any scalar field is zero vector. So this symbol is basically nabla. If you have nabla cross product nabla psi, you have the zero. So you can revise this. You can remember this. This one is from your previous mathematics class. So if you forgot, you need to open your textbook of the mathematics or calculus. So if you have nabla, you cross product with nabla and scalar, you will get a zero. Okay. So before proceed, I will explain to you some mathematical identity which is useful for you. Alright. For example, we have the curl. Okay, curl, C-U-R-L. The curls mean nabla cross product any vector. Let's say velocity. So this one is basically you have I. Okay, you have J and you have K. It is d del over del x and del over del y and del over del z. And below part here you have U, let's say U, V and W. Okay, so upper parts represent the nabla and then below part represent the vector identity of the velocity. So how to solve this? Okay, how it's represent in full form is basically, let me change the color. Okay, I maintain the color. So let's say for I you need to close this. Don't look at this. Okay, so you have del W over del Y. Okay, you have del W over del Y, del W over del Y. Okay, minus del V over del Z. Okay, so this one is for I. So how I get this? For I, don't look at I. Okay, so dw over dw over dy minus ddv over del z. So you get this one. Okay, and then for j plus, okay, j. So look at j. Okay, don't look at j. You close this one. Okay, so del w over del x minus del if you close at j, it must be k over I, because the order of cross product is I, j, k. It must be I, j, j, k, and k, k, I. So for j, you close this one. Okay, so you must be k times dengan I. K times dengan I. K times dengan I. Yang tadi, you have I. It's okay. J times K. Okay, J times K. But for J, you close this J. It must be K times J. You cannot add I times K. It will be negative. But if you close this J, it will be K times I. So del U over del Z. Del U over del Z minus, okay, minus del W over del X. Del W over del X. Okay, and then plus again 4K. Okay, 4K. So you close this K. Okay, you have I times J is okay, positive. So IJ del V del X. Del V del X minus del V del X, del U del Y. Okay, del U del Y. So this is the full form of your this curl. Okay, and then you have what we call as a gradient. If you have gradient, I change color. You have a gradient. Gradients mean the nabla any scalar, let's say u. Okay, so you have du dx I plus du dy j plus d du dz k. Okay, so this is gradient. Okay, so gradient you need to do for each scalar lah. If you have nabla v, you have dv dx, del v del y, del v del z. For the next things is that what we call as divergence. Okay, if you have divergence, it means that you have divergent. You have nabla dot product v. Okay, dot product v. You should have del u over del x plus del v over del y plus del w over del z. Okay. So this this is a vector identity for your vector or scalar identity for your revisions. One more. If you we have one more, which is basically as a Laplacian. Laplacian square. Okay, if you have a nabla, or you have square and you have v or u, you should have del squared. Laplacian, the del squared u over del x squared plus del squared u over del y squared plus del squared u over del z squared. So this one we call as a Laplacian. Laplacian. Okay. So this four identity is useful in this topic. So you know that vector identity nabla cross product nabla phi is equals to 0, where the curl of gradient, this one we call curl of the gradient of any scalar field is 0 vector, 0. Okay, this is identity. So if nabla cross product v is equals to 0, okay, this one is from your irrotational approximation. This one is for your vorticity. If you forget, you have to look again your previous lecture. Okay, so if for vorticity, for irrotational, you have zeta is equals to 0. So the short form is the curl of the velocity vector is equals to 0. Then v vector is equals to nabla phi. Okay, the vector can be expressed as a gradient of the scalar function phi called the potential function. Okay, so if nabla cross product v is equals to 0, then v is equals to nabla phi. Okay, so this one basically, if you put this inside this, Okay, because this one is same, right? This one is same. So you will get again this identity. Okay. So V vector is basically gradient of the scalar. Okay. So we can say that the region of irrotational flow are also region of potential flow. Okay. So if there are potential flow, that means there is a irrotational. Okay. So potential function is defined as V is equals to nabla phi. Okay, if I expand this, remember what we do previously, we have del phi over del x plus del phi over del y plus del phi over del z. This one is full notations. Okay. So it's same thing. If I write here, this one is for U, this one is for V, and this one is for Z. Okay, and for cylindrical coordinates, we have UR, U theta, and UZ. Okay, I hope you understand what is mean by UR, U theta, and UZ. If we have the flow like this, so your UR is the radius. Okay, U theta is U tangent. It's different if different for the xy plane, you have Ux and Uy. Okay, so we substitute, we prove that potential flow is the incompressible. So we substitute equation 1 into the incompressible continuity equations. So this continuity equations is also in short form. So you can expand this by del U del X plus del V over del Y is equals to 0 for two-dimensional equations. Okay, and then if we put this value, this term inside this term, what you get? You get nabla dot product nabla phi. Okay, this one, we put this one into this one, you get this one, and then nabla dot nabla, you get nabla squared phi. So this one, if I expand, you have this squared over this squared phi over dx squared plus d squared phi over dy squared plus d squared phi over dz squared is equals to 0. So equation, this one we call as a Laplace equation. I explained you in the earlier of the lecture. Okay. So advantage of irrotational approximations. Okay, we know that it's combined three unknowns, U, V, and W into one unknowns. Okay, instead of you have three unknowns, you have only one unknowns. Okay, what it means? Okay, basically for the real flow, you have what? Du over dx plus dv over dy plus dw over dz is equals to 0. So these equations, you have three unknowns, u, v, and omega. Okay, but for the potential function, you only have one equations. Okay, which is del phi over del x squared plus del squared phi over del y squared plus del squared w over del z squared is equals to 0. Okay, so instead of 3, you only have one unknowns. Okay, this mean by this statement. So various solutions are available for Laplace equation. You can open your previous calculus or mathematics textbook. You can solve Laplace equation for many techniques. Okay, given set urban equation, we can solve for phi regardless of the flow property. So much more easy. You have one equations, you have one unknowns, should be okay. But for this equation, you have three unknowns, but you have only one equation. Is hard to solve. Okay, let's say you have a steady 2D incompressible irrotational velocity field specified by its velocity potential function, okay, as shown. So calculate the velocity components of u and v. So how we want to solve this? So the given phi, so calculate the velocity component of u and v. So we know that velocity vector or psi is equals to, you have velocity vector, okay, you have velocity vector v is equals to nabla phi. Alright, so this one is basically is equals to del phi over del x I plus del phi over del y j. Okay, okay, this one is equals to, we know that, okay, v vector is actually u I plus v j. Okay, so we equate this one, okay, we should get u is basically d phi over dx and v is equals to del phi over del y. Okay, so how to solve this problem? What is u? So u is basically you partial derivative psi, you partial derivative phi over x. So you should have 6x plus 4y minus 2. Okay, and then v partial derivative phi with respect to y. Okay, this equation. So you have minus 6y plus 4x minus 5. So this is answer for question A. Question B, verify that velocity field is irrotational. What is mean by irrotational? Okay, irrotational means we have learned in previous lecture where zeta is equals to 0. For two-dimensional, this one must be zeta z. Okay, so what is zeta z? What is zeta? Zeta is equals to 2 omega z. Okay, which is del v over del x minus del u over del y. Okay, is it equals to 0? You have to calculate. So del v over del x is equals to, so you have v, del v over del x is equals to 4. Del u over del y is equals to, del u over del y is equals to 4 minus 4. So this one is equals to 0. So this one is irrotational. Okay,